multiply over and over. So I'll choose something like starting with 5, but this time I'll multiply times a half, and then times a half again, and then times a half again, and then times a half again. And you just keep on multiplying times a half. That's what we call a geometric sequence, because you're multiplying by the same number over and over. So times a half, and so on. So in this case, what you're interested in is the common ratio. What are you multiplying by over and over again? So we'd say R is equal to 1/2. That's the number that you're multiplying by over and over. That's called the common ratio. And what's the formula for the explicit? What's the explicit formula for the geometric sequence?
N equals
A sub 1.
A sub 1 R sub power N.
Yeah. And folks, notice that these formulas look pretty similar. They both have A sub 1, the common ratio, common difference, and then an N minus 1. So I mean, they're virtually the same formulas, except here you're adding and here you're multiplying, and here it's multiplying and then it's an exponent. But it's still the same basic components. Okay, so then in this case, we would say this is term 1, term 2, terms 3, terms 4. And once again, I could find the fourth term by plugging in 4 for n. So A sub 4 equals A sub 1, which is 5, times the common ratio, which is a half. And then I plug in 4 for n. 4 minus 1 is 3. So I have 1/2 cubed. So it's really 5 over 1 times 1/2 cubed. 2 times 2 is 4 times 2 is 8. So times 1/8. And that gives me 5/8. Which indeed is the fourth term that we expected, 5/8. Yep. So folks, we have this idea that we're going to study sequences of a particular type. We'll study sequences where you add the same number over and over. It could be a positive number or a negative number. And we study sequences where you multiply by a number over and over. And it could be positive, it could be negative, it could be a whole number, it could be a fraction. And we're interested in these sequences. The first thing you always have to do is find the common difference or the common ratio. And then you can use your formula to predict any term in the sequence. And what we'll learn today is how to add up a bunch of terms. Like what if you wanted to add together the first 100 terms? What would that sum be? Hector?
Yeah, would it be possible for us to go over question 5 in section 9.1?
Yeah. Yeah, in fact, if anyone else has questions, we'll do number 9.1, number 5. Any others?
Yes, wait, hold on.
Okay, you keep looking.
Let me just log in.
But I have one more question, folks. What's the difference between an explicit formula and an implicit formula? So what do we even mean by explicit? What does an explicit formula allow you to do?
Find the A of n.
Yeah, you can find any term you want immediately. So like if I wanted the 100th term, all I do is I just plug in the number 100, and whammo, I have my term. You know, I plug it into my calculator, but I'd have it. That's explicit, means that you can immediately calculate any term you like. But implicit, we learned the other day, implicit, another word of which was recursive, means you cannot just jump to any term you like. You have to do all the terms in order. So Nadine, this is personal for you here. To do an implicit formula, you can't just jump to like the 100th term and calculate it. You actually have to go in order, calculate the first term, then the second term, then the third term, then the fourth term, and just go in order. It takes a long time. So here's a classic example of an implicit formula, and that's the Fibonacci sequence. So folks, recall the Fibonacci sequence. It starts with the number 1 and 1, and then you add the two previous terms to get the next one. So 1 plus 1 is 2, and 1 plus 2 is 3, and 2 plus 3 is 5, and 3 plus 5 is 8. And this is an example of an implicit formula, because the only way I know what the next term is to add the two previous ones. 5 plus 8 is 13. So if all of a sudden I said, tell me what that term is, you have no idea, because you'd have to go all the way back here and keep going in order to get there. So that's a recursive formula, an implicit formula. You might say, Mr. G, that sounds like a bummer. Like, I don't like that. Why would I want to ever deal with an implicit formula? Explicit sounds much better because then I just know whatever term I want immediately. But the fact is that, especially in this case, the implicit formula, which we said was f sub n is equal to f sub n minus 1 plus f sub n minus 2, which just technically means the nth term is equal to the sum of the term before it plus the term before that, previous. Implicitly, that formula is pretty simple. It says, to get the next term, add the two terms before it. I want you to see this. This is the formula for the Fibonacci sequence, the explicit formula. This is going to blow your mind. The nth term of the Fibonacci sequence is 1 plus root 5 over 2 to the power of n minus 1 minus root 5 over 2 to the power of n all over root 5. That formula is insane. Okay, because first of all, just imagine finding the second term. First of all, we already know what the second term is. It's just 1. But could you even imagine putting a 2 right there and there? You'd have to square this, and then square this, and then subtract them, and then divide by root 5. All that work just to find the number 1. Let alone, what if you wanted the 100th term? Do you really want to plug in 100 right there? You're going to raise this thing to the 100th power? Oh my goodness. I mean, the only way you'd ever want to do that is with the calculator. And in fact, what?
Or unless you were in that house.
Yeah. In fact, even if I wanted the 100th term, I would think it could even be easier just to use the implicit formula and work your way there. So this is a very shocking formula, very surprising indeed, that is the explicit formula. And so that really demonstrates a nice difference between explicit and implicit. So even though explicit is powerful because you can jump to any term you like, implicit sometimes is conceptually more simple. All right. Oh, and by the way, speaking of Fibonacci, did we watch all that stuff about Fibonacci?
Yeah.
You watched the rabbits and all that?
Yeah, the golden shell.
Yeah. So I just wanted to share, I was trying to find the quote from the book yesterday. I couldn't find it anywhere. And I was like, I know I've seen the book. Where have I seen it? And I couldn't find it online. It's because I held it in my hand. I went to the ASU library one day just to find this book. And this is Fibonacci's Liber Abaci. And that's his book that he wrote in the 1200s to popularize the use of Arabic numerals and the decimal system in Europe. So this is the book, folks. Like, this is it. This is the book, the publication that changed the way Europe does math. If not for this person at this time, we'd be doing Roman numerals for math. So if you scroll in, this was on page 404. It says here, how many pairs of rabbits are created by one pair in 1 year? So this is the actual book. Now notice, he starts us off with 1 pair of rabbits. And technically, he should have had a previous entry before that to be 1, 1, 2, 3, 5, 8, 13. Man had 1 pair of rabbits together in a certain enclosed place. Already sounds kind of ominous. That sounds kind of wrong. As a pair of rabbits in an enclosed place. And one wishes to know how many are created from 1 pair in 1 year, when it is the nature of them, being rabbits, in a single month to bear another pair, and in the second month, those born to bear also. Anyway, so then he goes on and he proceeds to solve the whole problem in words. Oh my gosh, like he doesn't do any math equations ever. He's doing the whole thing in words. Isn't that crazy? So,
Will you review something like that in your studies?
well, write out a whole thing in words?
Yeah.
I just don't think that that's the way it's done nowadays. I mean, you got to keep in mind, he wrote this book and this passage at a time where people were doing math in Roman numerals. It was this book that popularized Arabic numerals. So he was speaking to a very different audience. Yeah, no, we wouldn't do this.
So he needed to explain.
Yeah, he was explaining himself. Exactly right. So anyway, there it goes on to the next page. And then he says, you can indeed see in the margin how we operated, namely that we added the first number to the second, namely 1 to 2, and the second to the third to the fourth, and the fourth to the fifth, and thus one after another until we added the 10th to the 11th, and getting all the numbers in the series. So it's just a nice little piece of history for you about Fibonacci. Fibonacci.
Do you know how long it took him to
Write the book? Oh,
30 years.
Yeah, who knows?
Yeah, printing technology was something.
Yeah, I don't know. But it took hundreds of years for it to catch on, right? I mean, like, nobody uses Roman numerals anymore. Even though, ironically, if you look inside the cover of a book, the year of publication is still often given Roman numerals. Have you folks seen that? I mean, I only have 1 book with me. I wonder if they do it. I mean, what a weird tradition, right? How weird that even today, is it true? No, mine doesn't give it.
I know most school books do. I'm not sure.
Yeah, I think it would have to be a slightly older book. But they did actually used to give the copyright date in Roman numerals. You can look for it. I mean, that was happening even in the 50s, 1950s. They would put the date in Roman numerals. But I mean, you know how we count Super Bowls?
Mm-hmm.
The Roman numeral. I mean, what is that all about? What?
You also count Rocky movies.
Yeah, and Rocky movies. There you go.
I feel like nowadays it's
Yeah, just to make it look fancy.
quinceañeras, you put the Roman.
Mm-hmm. Yeah. All right, but this of course reminds me of two really good jokes. What do you call a number that won't keep still?
Zero.
A Roman numeral.
Just like zero.
Very good, everyone. And then another one, this is a fun one. Why were the Romans so good at algebra? Why were the Romans so good at algebra? X is always 10. Because X always equaled 10. Because the Roman numeral for 10 is X.
Oh.
So X always equals 10.
It's my all-time favorite joke.
Yeah, it is a really good joke. I only learned that joke like a year ago. I couldn't believe it. All right, so folks, if anyone has any questions to ask about the homework, we're going to start with Hector. He said 9.1, number.
Can you go over number 4?
Yeah. 9.1. Wait, did you say number 4?
Yes.
Okay, I'll go in order. Here's number 4. This is an excellent example of a recursive formula. Now, folks, notice why it's a recursive formula. Because they're defining the nth term in terms of previous terms. That's what makes it recursive. See, if it was just the nth term equals some formula that has n in it, that would just be multiplication and arithmetic.
They give you your first term.
Yeah, and they give you the first couple terms as well. But instead, they're defining a term in terms of other terms, and that's what makes it implicit. So when we look at this formula, the first thing I would encourage you to do is write it out in English and say, well, what they're telling me is that if I want the nth term, so if I want any term in the sequence, what I have to do is look at the term right before it, and I want to look at the term before that, and add them together. Right? This is the Fibonacci sequence. They're just saying if you want the next term, you have to add the two previous terms. So they start us off, and they say the first term is 3, and the next term is 4. So already, just by using the Fibonacci method, we can already go ahead and generate the sequence. 3 to 4 is 7, 4 and 7 is 11, 7 and 11 is 18, 11 and 18 is 29, 18 and 29 is 47, and so on.
I hate 7-Eleven.
Yeah, who goes? All right, so there we go. Now, but what I'd like you to see is how to do it the proper way. The proper way would say, I already know a sub 2 and a sub 1, so the next number I'm interested in is a sub 3. So how would I calculate a sub 3? That means plug 3 in for ed. And if I plug 3 in for ed, 3 minus 1 is 2, so that's a sub 2. And 3 minus 2 is 1, so that's a sub 1. And what they're telling me is that the third term is the sum of the second and first term, which I already know because they gave it to me. 4 plus 3 is 7. Right? They gave me a sub 2 and a sub 1 to look at. So now if I want a sub 4, what do I do? I'm plugging in 4 for ed. So I come over here and I let n equal 4. So that means 4 minus 1 is 3. And then over here, 4 minus 2 is 2. And now that tells me that the fourth term is equal to the third term plus the second term. And I know the third term now because I just computed it. And I know the second term because they told it to. And so 7 plus 4 is 11. And you can see we're generating the terms that we already did by just doing it Fibonacci-ally. Emily, how do you feel about that? You asked for this one.
Yeah, I'm so confused.
You
Okay,
asked for
Emily,
this.
Emily, we know the third and fourth term. How do I find the fifth term? What do I let n equal?
Okay,
Equals
it's
5.
Very good. And so now put 5 here.
Oh, okay.
Put a 5 right there.
5 minus 1. I mean, 4.
4. Now put a 5 here.
It's your question.
Put a 5 here.
Let the one-
5 minus 2.
Okay, so
Okay, so you
the
have
fifth term is the fourth term plus the third term. What's the fourth term?
The 14 is 11.
11. Now what's the third term?
3, 7.
Yeah.
Oh,
See, there's a
that's
difference.
right.
See, that's just, this is the name for the third term. That's the actual third term.
Oh, okay. This is I was watching the
So there, the fifth term is 18.
Okay.
Wait, so that makes sense. How do you find the
Hey, you want me to raise your hand?
They tell you. They tell you right there. The
first?
first term is 3, and the second term is 4. That, you call these the seed terms. They seed the sequence. You need the first 2 in order to start the sequence going. Nadine, what other question do you want to ask? I mean, you're jumping right in.
Yeah.
But no, seriously, does that make sense?
Yeah.
Okay, so that was number 4. Hector asked for number 5. So at number 5, Is this sequence arithmetic? So, what you'd want to do is investigate. Is this sequence arithmetic? So we've got a sub n equals, I'm going to rewrite it as 9n plus 9. And so I'm just going to start looking at terms, right? So if I want the first term, I let n equal 1, and I plug in 1 where I see n. That's how I calculate the first term. And so 9 plus 9 is 18. So the first term is 18. How do I get the second term?
Two.
So 9 times 2 was 9. And so that's 18, so it's 27. Emily, how do I get the third term? 36. 36. And Melania, how do I get the fourth term? Yeah. So now, what we see here now, folks, is I have the sequence which is going 18, 27, 36, 45. What am I adding by every time? Yeah, I'm just adding 9, adding 9, adding 9.
No, I said no in German.
Oh, 9. So is this arithmetic? Yes, by definition, arithmetic is when you add over and over and over again. So yes, it is arithmetic. And then they want to know the first term and the common difference. Well, we've got all that. The first term is 18, and the common difference is 9. Now, this is a little bit more advanced, but I think it's kind of fun. We also know it's arithmetic if it follows the formula. It's arithmetic if it follows the formula. A sub n equals a sub 1 plus d times n minus 1. Okay? And I could go ahead and rewrite that right now and call that a sub 1 plus dn minus d, and then bring the dn out front. So it'd be dn plus a1 minus d. So a sequence is arithmetic if it's equal to a number times n plus another number. And that's what that sequence is, 9n plus 9. That's the common difference was 9 times n plus just some number. Because first term minus d is just a number. So sure enough, any sequence will be arithmetic if it's of the form a number times a variable plus a number, which of course is, yeah. So a sequence is arithmetic if it is linear. So automatically, yeah, that thing is arithmetic because it's linear.
I have another one, but it's not as simple as the one we just did.
Okay.
It is an equals 1 over 3 plus 7n.
Yeah, so is that thing arithmetic, folks?
No, the 1 is over everything.
Oh, okay, is that arithmetic? 1 over 3 plus 7n? Okay, so folks, is 1 over 3 plus 7n linear? Is that mx plus b?
No.
No, it's not, because it's 1 divided by that. And there's no way to rewrite that. Now, furthermore, you can just try a couple, right? Hum a few bars. The first one is going to be 1 over 3 plus 7, which is a 10th. And the second one is 1 over 3 plus 14, which is 1/17. And then the third term would be 1 over 3 plus 21,
Yeah.
which is 1/24. Now, are those adding the same amount both times? How do we know? How do you find out how much you added to go from here to here, and how much you added to go from here to here? You just subtract. I can just do this one minus this one and see what the difference was.
Oh,
In fact, that's why it's called the common difference. Because you take the difference, you go this one minus this one, what's the difference? This one minus this one, what's the difference? So watch, if I actually do, using my math frac button, 1/24 minus 1/17, that's a difference of, -7 408ths. So apparently I added 7 408ths to get from there to there. So then what's 1/17 minus 1/10? That was a difference of 7 170ths. So from here to here, I added that. From here to here, I added this. Is it the same? No. So it's not arithmetic. Actually, does that make sense? Great. Good questions. One more?
I haven't gone to the 9.1. I mean,
Well, I tell you what.
9.2, 9.2.
Folks, when we take our break, other than taking your break, scroll through and see if you have any other questions to ask. Otherwise, we're going to keep going here. I do have a couple jokes for you, I think. Now let's see. Man, I continue to fail to update my calendar. This is the right calendar. Today's the 24th. We're finishing chapter 9. On Monday, you take a test. So that means your practice test is due on Monday. Well, you should already have copies of the practice test. I hope you do. I posted it online, so it's on Canvas under announcements, so you can print another one out. I also posted the solutions. So on Monday, come into class with your practice test done. Of course, I'll collect it for a grade, and then you'll take your test. That's the practice final exam. So that's Monday. On Wednesday of next week, we will practice for the final exam. So did everyone take a practice final? This is your practice final. Does anyone need one?
I do it.
You got one? You got one? Hector, you got one? Oh, there you go. Yeah. So that's your practice final exam. So we're going to go over that next week on Wednesday so that you see all the different types of problems that you can expect to see on the final. Now, folks, the practice final exam is not a line item in your grade book. That means I'm not going to collect it, and I'm not going to give you a grade for it. But that doesn't mean you shouldn't do it. No. Well, yeah, you will get extra credit because you'll score higher than on your exam than if you don't. Right? So that's kind of extra credit right there, isn't it? Plus, the fact that I'm giving you a practice final exam is essentially letting you see the final exam ahead of time.
Yeah, like,
I mean,
what are you
it
asking
would
for
be
more?
pure crazy town not to finish the entire final exam before you come in and take the final. Right? I'm not calling you crazy. I'm just saying, why wouldn't you finish the whole practice final before coming to take your final? You know, that's the difference between going in blind and actually knowing every problem is going to be on the test. So you're all going to do the practice final exam. I will post the solutions online as well. So you can just go online and look at the solutions. Okay, and then finally you'll come in on Wednesday. I believe it's the same time, same room. There will be an online course survey that I publish next week. It's really helpful to me to hear your feedback. So before you come in and take the final exam, go online, take the course survey. I'll make it the first thing you see on Canvas. And I ask that you take it before you take the final exam. So, you know, it's easier to take it at home. But if you come in and take the final exam and you haven't done the course survey yet, I'll have you use my computer or your phone, do the course survey real quick, and then I'll hand you your final exam. So that's your ticket to the final exam.
Is it worth it?
Yeah, actually, it's worth 2 extra credit points. Ooh la la. All right, now. Where are we? Oh yeah, that's it. So did I tell you about the dog joke? What does a dog do?
No.
Oh goody. What does a dog do that a human steps into?
You do.
Pants! What does a dog do
It's priceless.
that a human steps into? Maybe. No, okay. I'll tell you one more because this is Wednesday. This is just a one-liner. Jokes about German sausage are the worst.
Oh, worst is the
Worst?
sausage, yeah.
They're the worst.
Oh.
Jokes about German sausage are the worst. All right. Okay, so here we go, folks. We're starting. This is where we are, right? Did we finish up through 9.1 or did we not? Maybe we didn't. You tell me, where did we get to? Okay, we need to go back to 17. That's right, we had a couple more to do. Oh, good, and there's such a good one too. Oh, these are so good, folks. Okay, I'm so excited about these problems. Let me tell you why.
Oh, there was a problem with that.
Oh, good. I'm glad that we can go over it. Now, somehow in America, and probably in other countries too, we get this idea in our head that we should be able to solve a problem just by looking at it. Like, just by looking at it. Or better yet, the answers are almost always on the ceiling, I hear. So if you look at it or look at the problem, it'll come to you. That's not true. Problems don't just come to you. You need to rewrite it and rewrite it and rewrite it. We've talked about the power of rewriting. You rewrite something into a different form because it gives you insight. So just look at this pattern. This is such a good pattern. It's such a good pattern. So I claim that there's a pattern here. 1 2/3, 1/3, 4/27. What is the next term? And furthermore, what is the formula for these terms? Now, fortunately, both of those questions will be answered simultaneously, because if you can guess the next term, that means you know the formula for all the terms. So what do you think, folks?
One.
I'll ruin it for you right now and tell you that it's not arithmetic or geometric. This is just a sequence.
Oh.
And we're just trying to figure out what is happening.
You ruined the end.
Yeah, well, because I figured you'd start subtracting and find common differences or something there.
I knew there was nothing different about it. Well, there is something different about it. But they're not similar at all.
It doesn't make sense.
Very good, Valeria. It does make
Makes
sense.
sense.
Absolutely. And so what we want to do is start making it make more sense. So we look for clues and we think, how can I rewrite that? So first of all, 3 of the 4 terms are fractions, right? So what would be one helpful rewrite? Make this one a fraction, right? Now, one thing we've talked about is analyzing the numerator and the denominator separately. So let's just look at the numerator for a second. 1, 2, 1, 4. Any possible patterns there? Or anything that you wish, like, man, I wish that were this.
Can we move like the one
You cannot move terms. No, that's not allowed.
There is
Good
one,
question.
there is one thing about them that's similar.
What?
They've never skipped over repeating and then you put it calculator.
Sure, perhaps. Yeah, so just look at the numerators for a second, okay? First of all, could that be the pattern? Could it be 1, 2, 1, 4, 1, 8, 1, 16? Maybe. Be a pretty weird formula. But now look again at 1, 2, 1, 4, and if you could just change one number so that you could have a really solid sequence, what would it be? Yeah, wouldn't you like a 3 right there? Because then it would be 1, 2, 3, 4. And you'd be like, yeah, that's a good pattern. Okay, so this is a heart and soul of math, is that you can rewrite things. You have flexibility and creativity. You can change things if you want to, if you know the rules. So how can I rewrite that so that's a 3? How can I rewrite the fraction 1/3 so that there's a 3 on top? Yeah, well, I heard a bunch of sounds. Well, you can't just do a reciprocal for fun.
3 9.
Yeah, you can rewrite. Okay, so now I have 1 over 1, 2 over 3, 3 over 9, and 4 over 27. Now let's look again. Do we have a really good pattern in the numerator? Yeah, we have a great pattern in the numerator. 1, 2, 3, 4. What's the next term going to be? 5, right? So, so we hope. Now let's look at the denominator. We've got a 1, a 3, a 9, a 27. Do you recognize these numbers? What are they? Very good. Not multiples of 3. That'd be like 3, 6, 9, 12, 15, 18. Powers of 3. So 3 to the 0. So here, I'm going to rewrite this again. 1 over 3 to the 0. 2 over 3 to the 1. 3 over 3 to the 2. 4 over 3 to the 3. And therefore the next denominator would be?
81.
Yeah. Now, is this pattern painfully obvious?
Yes.
Pretty painfully obvious. Now, watch, we're going to go one step further here. So this was the first term. This was the second term. This was the third term. This is the fourth term. This is the fifth term. I want the nth term.
Okay, the beginning term?
Not the beginning term, the nth term. You know, just the nth term represents the formula or the structure, but then you just plug. The first term is 1. The second term is 2. The third term is 3. The fourth term is 4. The fifth term is 5. The nth term will be the nth term will be n, right? Now let's look at the denominator. The first term is 3 to the 0. The second term is 3 to the 1. The third term is 3 to the 2. The fourth term is 3 to the 3. The fifth term is 3 to the 4. What's happening here? 3 to the, well, it's not the same number. It's the first term, the power is 0. The second term, the power is 1. The third term, the power is 2. The fourth term, the power is 3. The fifth term, the power is 4. I mean, just look at these two numbers. What's the relationship between 0, 1, 1, 2, 2, 3, 3, 4, 4, 5? Is what? Yes, the previous number, isn't it? Or another way of saying it is the relationship between 4 and 5 is that it's 5 minus 1. And that's it. That right there is our nth term. A sub n is equal to n over 3 to the n minus 1. That tells you the structure of the entire sequence And it is the formula that will tell you the next term. We already guessed what the next term would be. And again, if we plug in 5, that would be 5 over 3 to the 5 minus 1 is 4. And indeed, that would be the next term. If we want the 6th term, we plug in 6. So that would be 6 over 3 to the 6 minus 1, that's 6 minus 1 is 5, 3 to the 5th. And that would be the next term. So folks, this is kind of like an example of you create a message that's clear as day, but then you simplify it, and then it becomes not clear. Kind of like cryptography, encoding a message. So watch, just so you can all really appreciate this. I'm going to make a new pattern, and I'm just going to call it n over 2 to the n minus 1. Okay, it's almost identical. So watch now, we're going to create the first, second, third, fourth, and fifth term. So what happens if I plug in a 1? 1 over 1 minus 1 is 0, 2 to the 0 is 1. So there's the first term. Now plug in a 2. 2 over 2 to the 2 minus 1 is 1. 2 to the 1 is 2. Now plug in a 3. 3 over 3 minus 1 is 2. 2 squared is 4. Now plug in a, what was that? 1, 2, 3. Plug in a 4. So it'd be 4 over 4 minus 1 is 3. 2 cubed is 8. We'll just do one more for good measure. Plug in a 5. That'd be 5 over 5 minus 1 is 4, 2 to the 4th is 16. So that's my pattern so far. And even better, what if I had written it as 1, 2, 3, 4, 5. And then down below I wrote 2 to the 0, 2 to the 1, 2 squared, 2 cubed, 2 to the 4th. Now if you walked in and you saw this pattern right here, do you think there's anyone who wouldn't be able to write down the next term? What's the next term? 6 over 32? Yeah, right? Plain as day, right? But now watch. As soon as I take these terms and simplify them, 1 over 1 is 1. 2 over 2 is 1. 3 fourths is 3 fourths. 4 eighths is a half. And then 5 sixteenths. Now, who in the world, if they walked in, would look at that and be like,
I know the answer.
oh no. The next term is so obvious. It's 3 sixteenths. Like, no one would ever predict that, right? It would be completely hopeless. If you saw this pattern, no one would just look at it and say, oh yeah, 3 sixteenths. Even though that is what it is, because 6 over 32 simplifies to 3 sixteenths. Yeah, so the next term really is 3 sixteenths, but it's not obvious anymore because it's simplified. Okay, so folks, is this pattern obvious? Is this pattern obvious? No. So what's your job? To take this pattern and rewrite it so that the pattern is obvious. So how do we rewrite things? How did we do it? How did we rewrite? What were some things we did? We turned whole numbers into fractions. We turned one fraction into an equivalent fraction. And why did we even do that? Because we looked at the numerators and we were like, gosh, I hope that said 1, 2, 3, 4. Right? It was a hope. It was a prayer. Right? I mean, it wasn't even a sure thing. We just tried it. Okay? This is so important. In math, sometimes you just try things, right? You're clueless. You don't know how to solve a problem. Try something. Because you never know what'll happen, right? I mean, really, this is a motivational speech for everything in life, isn't it? We're not just talking about a particular number problem. You just have to try something until it works. Okay, so you all try the next one. The next one is not at all like this one, but you know, I still want you to try things. Just play around with the numbers. See what you come up with. Because some of those numbers you should recognize. And see, again, right now we're looking at this pattern, and it might not be obvious in the way it's written. Fascinating. What do you do with your calculator? Like, what are you attempting? Okay, and powers, or what goes into the numbers? Sure. Did anyone find any divisors or things that divide into those numbers?
Not quite yet, but I know they're all powered by 3.
What do you mean?
Well, each one is a power of 3. It's like, I did 3 squared, 3 cubed is 27.
Yeah.
4 cubed is 64, and then 5 cubed is, of course, 125. I guess 6 cubed is, yep.
Okay, so folks, did any of you hear what Hector just said? Hector started with just a random observation that he recognized that 27 was 3 cubed, right? So from there, there's a couple ways this could have happened. Like if we're thinking about a pattern, maybe the pattern was going to become 3 cubed, 4 cubed, 5 cubed, 6 cubed. You know, just maybe. Or maybe the pattern was going to go 3 cubed, 3 to the 4th, 3 to the 5th, 3 to the 6th, right? Or maybe the pattern's something else completely. But again, it's a wing and a prayer. You know, you like just try something. From a random observation that 27 is 3 cubed, that at least gives you a starting point. And then he proceeded to just check, and sure enough, 64 was 4 cubed, and 125 was 5 cubed, and 216 was 6 cubed.
I checked the bottom one.
Yeah, the bottom ones don't work.
Yeah.
So what's the next term in the series?
Well, one thing could be possible because like we see that one of them is linear, so maybe it would be n cubed.
Right, but specifically, what's the very next term? 3 cubed, 4 cubed, 5 cubed, 6 cubed, 7 cubed, 7 cubed, and then somewhere down the line, n cubed. Now,
343.
right, that's 7 cubed. But now, to be fair, folks, remember, we can't just jot down the formula yet. We're saying this is the first term, this is the second term, this is the third term, and this is the fourth term, and this is the fifth term. So if I wanted to say what the nth term was going to be, you have to look at the relationship between the numbers that you see. So clearly the power is always a 3, so the nth term will be something.
Actually, no, maybe we know the power is 3, and we know the first term is that, so maybe it would be n plus 2 squared, n plus 2 cubed. This would be my formula.
Yeah, and that's correct, because whatever the term number is, you add 2 to it, and that's the number you cube. So the second term, 2 plus 2 is 4, and you cube it. The third term, 3 plus 2 is 5, and you cube it. The fourth term, 4 plus 2 is 6, and you cube it. So the nth term, n plus 2, and you cube it. And that's the answer, folks. The answer is n plus 2 cubed. Now again, this is not obvious, but it should be playful rather than
Frustrating.
yeah, exactly. Now, the only way though that this becomes playful is as you develop your number sense and you start recognizing numbers. You know, I gave you a packet last month that had 27, 64, and 125 on it. You saw, all of you saw those numbers. You knew that this was 3 cubed. You saw this as either 2 to the 6th or 4 cubed. You saw this as 5 cubed. So you've seen these numbers before. And if all you had under your belt at this point was the fact that this one was 3 cubed and this one was 2 6th or 4 cubed and this one was 5 cubed, you'd be able to say, well, heck, I've seen these numbers before and they all appear to be cubes. And then that would give you the hypothesis, 3, 4, 5. Check your calculator. Is it 6 cubed? And the answer is yes. So, see, this isn't like obvious. It's just like doing experiments and hypotheses.
It's not easy. It's not hard.
It's what makes math fun.
Yeah. And again, yeah, if the attitude was, this is a puzzle I need to solve, rather than this is stressful and stupid fractions.
Where's the 2?
What 2?
The n plus 2.
Okay. We're calling this the first term. We're calling this the second term. This is the third term, the fourth term, okay? One thing we know is that the power is always a 3. So that doesn't change, it's just 3. So what's the relationship between the first term being 3, the second term being a 4, the third term being a 5, and the fourth term being a 6? What do you do to this number to get that number? Uh-huh. Yeah, so if you want the nth term, the base would be n plus 2. Okay, does that make sense? Okay, very good. Yeah, so I mean, the problems that we've seen right here, it's not one particular method, one particular rule that will help you, other than trying to restructure the form of the numbers to find a structure that fits every time. Like, what was the structure here? The structure was a number over 2 to a power. Like, that was the structure right there. Whereas here, the structure was a number being cubed. And then from there, you move on. So what we're really doing with is playing with the idea of restructuring numbers to have the same structure. Okay, folks, we're now starting 9.2. We're going to continue to work on restructuring a number. We're taking a group of numbers and rewriting them so they all have the same structure. In fact, here, I want to give you 2 more examples so it becomes a little more obvious. Consider the numbers 1, 4, 9, 16, 25, 36. What structure makes all those numbers look the same? Or at least start by just telling me what are those numbers. These are the square numbers. These are square numbers, right, folks? 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, right? And if this is the first term, second term, third term, fourth term, fifth term, sixth term, the nth term would be n squared, right? And what's the structure we're looking at? It's something squared. That's the structure. So now everybody, we'll watch real close here. What if I gave you the sequence 2, 5, 10, 17, 26, 37? What is the structure we're looking at? I chose this sequence because it's related to the first sequence. Here are these 2 sequences. Compare 2 to 1. How do you get 2 from 1? How do you get 5 from 4? Add 1. How do you get 10 from 9? Add 1. How do you get 17 from 16? How do you get 26 from 25? How do you get 37 from 36? So how could I rewrite these numbers? I could rewrite 37 as 36 plus 1, right? And I could rewrite this as 25 plus 1. And I could rewrite that as 16 plus 1. And I could rewrite that as 9 plus 1. I could rewrite that as 4 plus 1. I could rewrite that as 1 plus 1. So then how can I rewrite that? 1 squared plus 1, 2 squared plus 1, 3 squared plus 1, 4 squared plus 1, 5 squared plus 1, 6 squared plus 1. And therefore, if this is the 6th term, what's the nth term?
N squared plus 1. So put the n.
You can put the parentheses and no parentheses, because it's just n that's being squared. Yeah, the key thing is that the structure that we're talking about is something squared plus 1. I took every single number here, 2, 5, 10, 17, 26, and 37, and I rewrote it as something squared plus 1. Okay, one more. This is your bonus here. We're all going to get it. How about the pattern? Negative 1, 2, 7, 14, 23, 30.
No, it's not
Close
plus
enough.
1. N minus 2.
It's not n.
I mean, n squared minus 2.
Yeah, and then squared minus 2. How do I rewrite these numbers? Like 34 is actually 36 minus 2, right? 23 is really 25 minus 2. And 14 is really 16 minus 2. 7 is really 9 minus 2. And 2 is really 4 minus 2. And negative 1 is really 1 minus 2. So now I have my squares there. And now I rewrite that as 1 squared minus 2. Like 2. That'd be 2 squared minus 2. 3 squared minus 2. 4 squared minus 2. 5 squared minus 2. 6 squared minus 2. So if this is the 6th term, what would the nth term be? So So is this making more sense about what I'm saying about restructuring a number? Finding a structure that applies to all of them. That's kind of what we're talking about when we look at a sequence. We need to find a structure that would rewrite every single number in terms of the counting numbers 1, 2, 3, 4, 5, 6, all the way down. And once you can do that, once you can restructure a sequence into the same structure using the counting numbers, you've defined your sequence.
What if your sequence didn't have wasn't whole numbers?
Well, you gotta get the counting numbers in there somewhere. You gotta have the numbers 1, 2, 3, 4, 5 in there somewhere because you're saying it's the first term, second term, third term, fourth term. So somewhere, somehow, you have to restructure the sequence into a formula that uses the number 1, and the number 2, and the number 3, and so on. Okay, so let's try it. Everybody. Start with number 1. We're gonna consider a couple ideas here. First, we have this nice new symbol up there. Called what? What is that symbol? It is summation notation. That symbol is used to mean summation. Summation or sum starts with the letter S, and this is the letter S in what language or what alphabet? Greek. It is the Greek alphabet. And that is the Greek letter S. So if you wanted to write summation, well, the word sum, that's the letter S. So this means sum, and what are we summing in number 1? Number 1, we're finding the sum of numbers of the form 5g plus 3. Okay, so that's the structure. The structure is 5 times something plus 3. 5 times something plus 3. 5 times something plus 3. And what are we going to let g equal? We're going to start by letting g equal 4. That's your starting number. And you're going to work your way up 4, 5, 6, 7, 8, 9. You're going to end with 9. So that's what that symbol means. It means we're going to add up a bunch of numbers, each of which have the form 5g plus 3. 5g plus 3 really just means a multiple of 5 plus 3. That's what that means, a multiple of 5 plus 3. So what are the multiples of 5? 5, 10, 15, 20, 25, 30. We all know multiples of 5. And then add 3 to all those. So 5 plus 3 is 8, plus 3 is 13, plus 3 is 8, plus 23, plus 3 is 33. These numbers right here are multiples of 5 plus 3. These numbers are of the form 5g plus 3 because they are multiples of 5 plus 3. Okay, so that's what we're going to do. We're going to take numbers of the form 5g plus 3. And we're going to add them all together, provided we let g equal 4, 5, 6, 7, 8, 9. So now how many terms are we going to add together? We start with 4, 5, 6, 7, 8, 9. How many terms? Yeah, 6. So everybody watch how we're going to do this, right? Equals? I don't have enough room there, so I'm going to write equals. We're going to add together 6 terms. 1, 2, 3, 4, 5. Wrote that for me. Because I want Valeria to see. 1, 2, 3, 4, 5, 6. Okay, everybody start writing. This notation here means we're about to add together 6 terms, because counting from 4, 5, 6, 7, 8, 9, that's 6 terms. Each of those terms are going to have the structure, the form 5g plus 3. And we're going to let g equal the numbers 4, 5, 6, 7, 8, 9. Now we're not going to do this in our head. I want you to see it very clearly what's happening. Inside each of these parentheses, I'm going to write the structure 5 something plus 3. 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 Right around now, that a variety of students, especially students I've got in high school, would say, "Ooh, really?" And I would say, I promise your fingers won't break. Your fingers are not going to snap in half. Okay, so you see what we're doing. We're adding together a bunch of numbers of the form 5 something plus 3. And what numbers are we going to plug in?
4, 5,
Exactly that. 4, 5, 6, 7, 8, 9. So now we can go ahead and we can do a lot of that in our head. So for instance, 5 times 4 is 20 plus 3 is 23. And then 5 times 5 is 25 plus 3 is 28. 5 times 6 is 30 plus 3 is 33. 5 times 7 is 35 plus 3 is 38. 5 times 8 is 40 plus 3 is 43. 5 times 9 is 45 plus 3. Now notice, I have a sequence of numbers 23, 28, 33, 38, 43, 48. And those numbers are just numbers, and we might look at them and say, gosh, what structure would make them all look the same? And that structure is 5 something plus 3. I can rewrite all of those in the structure 5 something plus 3 by just plugging in the counting numbers 4, 5, 6, 7, 8, 9. So 5g plus 3 is a structure that gives meaning to this sequence. Yeah, well, now we just add them together. Yeah, you just add those together in a calculator. Plus 23 plus 28 plus 33 plus 38 plus 43 plus 48. We have 213. Yep, that's the answer. So like in those couple of problems we started with, we were figuring out the structure. They're just coming right out and telling us the structure. They're telling us the structure right up front, so we don't have to try to figure it out. They're just telling us the structure. So let's look at what?
In real life, where we use this.
Oh, every day. Go to the grocery store, getting gas, buying a puppy. I'm kidding. I mean, where in real life are you going to look at a mystery and have to figure it out? Only every day. But I mean, this particular mystery, probably never again the rest of your life.
Okay. I was
Right.
going to do like that.
I don't know, I think a lot of people would want to buy doing it.
Yeah, exactly. Yeah, I mean, Olivia, the question, when will I do this skill in my life? Maybe never. But when we use critical thinking to solve a mystery, every day. And that's what we're doing. Math is just a metaphor for using critical thinking to solve a mystery. You know, we're trying to solve a mystery about things called sigma and numbers.
Might even
But
Use math to solve. I guess you're using math to solve this.
yeah, exactly right. Okay, so let's try number 2. We've got sigma notations. We're going to add up, starting from I equals 1. Now you're allowed to use whatever letter you want to be your index. We call this the index. Your index number, we're going to plug in the numbers 1, 2, 3, 4. So we're only going to have 1, 2, 3, 4 terms. So the structure of those terms is 1/4 I squared plus 1. So the first thing we're going to do is just by looking at the index, starting at 1, ending at 4, 1, 2, 3, 4, 4 terms, I'm going to write parenthesis, plus parenthesis, plus parenthesis, plus parenthesis. Because I know I'm going to be adding together 4 terms. Another way of looking at what we're doing is this is a detail-oriented skill that requires extreme care, patience, diligence. When will you need that? Every day of your life. Okay, so we're going to write in the structure now. What's our structure? The structure is, and this is going to feel pretty detailed here, 1/4 parenthesis, parenthesis squared plus 1 parenthesis. That's the structure. 1/4 times parenthesis something squared plus 1. So 1/4 parenthesis something squared plus 1 parenthesis. Whenever I say something, I mean parenthesis. So 1/4 parenthesis something squared plus 1 parenthesis, and 1/4 parenthesis parenthesis squared plus 1 parenthesis. Now there's another skill, the ability to see what is there and write it down correctly over and over and over again. Again, it requires an eye to detail and patience. Any of you ever hear about the Mars orbiter? It was NASA launched this thing. It's called the Mars Atmosphere Orbiter or Mars Weather Orbiter. Anyway, they sent a thing to Mars, and it cost millions and millions of dollars. The orbiter gets all the way to Mars, and then boom, crashes right into the planet and is destroyed. Yeah, super sucks. And the reason is because when they were making the thing, they converted from inches to centimeters incorrectly. All right? So there you go, millions upon millions of dollars, successfully launched a rocket, successfully sent to the orbiter all the way to Mars, successfully got to Mars, and then crashed right into it.
You mean successfully crashed?
Yeah, successfully crashed into it. So, I mean, again, do you know what a simple mathematical mistake that was that they made? Big, easy, simple mistake.
I'm sure some people got fired.
Oh yeah, I'm sure people will. Okay, so now we plug in our numbers. Our index numbers are 1, 2, 3, 4. So now we plug in 1, 2, 3, 4. And now we go about doing some computations. Now, When we deal with things like this, we'd like to try to be strategic. So I want you to notice, do you notice what each of those terms has? A 1/4. And therefore, could we factor the 1/4 out? Absolutely we could. We could bring out the 1/4 from each of those. Okay, so bring the 1/4 out, so that now each of my terms is just 1 squared plus 1 plus 2 squared plus 1. Let's still have plus parentheses. Plus 3 squared plus 1 plus 4 squared plus 1. Now doesn't that look nicer? We just pull that 1/4 out of there. Now we don't have a whole bunch of 1/4s, we just have one 1/4. And so now, even easier, we can do all this in our head. In fact, this is the sequence we just looked at. So 1 squared is 1 plus 1 is 2. 2 squared is 4 plus 1 is 5. 3 squared is 9 plus 1 is 10. And 4 squared is 16 plus 1 is 17. Now we can just add up all those whole numbers. It's 34. So 1/4 times 34. Which, putting it over 1, we get 34 over 4, which is 17 over 2, which is 18.2, which is 8.5. Valeria wants to know when she'll need to do this in her real life. One time is gonna be next Monday when you take your test. Another time is gonna be the Wednesday after that when you take your final exam. That's twice. All right, we're gonna do one more before we take our break. Bow. What are you doing? That's cheap.
That was funny. There's also another time you can take this during your next math.
During the next math class. The funny thing is, as a math teacher, when someone asks, when am I ever going to need this in my life? I always feel like they're asking me the question, what excuse have you for living? I can just imagine going to one of my own math teachers. Like, I'm in math class right now. I should send a message on the discussion board. They're like, dude, doctor, what excuse do you have for living? Honestly. Don't worry about it. I'm just kidding. All right, number 3. So we're going to sigma from n equals 1 to 5. And this time the structure is something you might not have seen for a while. N plus 1 factorial over n factorial. So factorial, does anyone remember what factorial means? Factorial, I'm going to give you an example. 5 factorial would be starting with the number 5, and then you start counting down through multiplication until you get to 1. 5, 4, 3, 2, 1. That's 5 factorial. It's just a compact way of saying, start with the number 5, multiply by every whole number below it until you get to 1. So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1 is 120. 5 factorial is equal to 120. Here's another example, 4 factorial. That'd be 4, 3, 2, 1. Multiply them all together. 4 times 3 is 12, times 2 is 24, times 1 is 24. Here's another example, 3 factorial. 3, 2, 1. That'd be 3 times 2 is 6, times 1 is 6.
About 0 factorial.
Ah, yeah, so you
Yeah,
got all the way
I
down
think
to 2
that's the sum,
factorial is 2 times 1, which is 2, and 1 factorial is 1 times 1. 0 factorial, by definition, is equal to 1. That's just a definition that mathematicians have all agreed upon because it makes all the formulas work.
What about negative 5?
I think there is a way to do factorial for negative numbers, but it's not applicable.
You're not really supposed to be doing negative factorials, honestly.
Well, wouldn't my answer just be this? Since 5 is an odd number, then you can still get the same answer, just be negative.
No.
120?
There's just a completely definition that a different definition takes over if you're factorializing a negative or a decimal. We don't do it.
Actually, I believe if you put in your calculator, it'll come up as an error.
Yeah, it should be an error.
It doesn't make a difference even if you multiply from 1 to 5.
Right, you just have to multiply all the numbers together. Now, this is on your calculator. When would you do this in your real life? Every question that has to do with probability, permutations, and combinations, come back to this formula. So you actually use this formula a lot.
So if you go to 142,
Yeah, math 142. Okay, so let's go and do this. What's our structure? We're gonna do 1, 2, 3, 4, 5. There's 5 terms, so it's gonna be something, plus something, plus something, plus something, 1, 2, 3, 4, plus something. And plugging in our numbers, so we're doing plus 1 and then over n. So using 1, 1 plus 1 is 2 factorial over 1 factorial. Then 2, 2 plus 1 is 3 factorial over 2 factorial. And then 3, 3 plus 1 is 4 factorial over 3 factorial. And go to 4, 4 plus 1 is 5 factorial over 4 factorial. So one of the messages that I'm giving you in this class is the power of rewriting. Also the power of playfulness and playing around with things and messing around with things and rewriting things. And jokes about math. So if you just went in right now and did these by hand, okay, 6 factorial is 6, 5, 4, 3, 1, which is 720. If you did it by hand, it's going to be unfortunate. Because it would be 2 over 1 plus 6 over 2 plus 24 over 6 plus 120 over 24 plus 720 over 120. And then, you know, just math. Take all those, type them all into your calculator and see what you get. However, we don't have to do that. Because just take a look at that last term. 6 factorial over 5 factorial. Everybody watching? What if we actually write that out using the definition? So 6 factorial is 6, 5, 4, 3, 2, 1. And 5 factorial is 5, 4, 3, 2, 1. What can you do?
So leave more and answer the question.
What can you do with all those? Anything you have on top and bottom? Yeah. And the answer is 6. So what's 5 factorial over 4 factorial? That's 5, 4, 3, 2, 1, all over 4, 3, 2, 1. That's just fine. So all of this, forgetting that, you can just say the answer is 2 plus 3 plus 4 plus 5 plus 6. So that'd be 5, 9, 14, 20. That's why I love factorials. Yeah, factorials are nice. They have a lot of canceling. At some point, you might have been exposed to the factorial. Yeah.
High school, the different districts have different curriculums.
Yeah, different districts do things differently, different schools do things differently. And furthermore, there's, you know, the 80-20 rule in high school, which is that you spend 80% of your time doing the curriculum and 20% doing something that could be, you know, optional but interesting and math related. So, you know, depending on what school you went to, you might or might not have seen certain skills.
Yeah, you don't even really learn, you don't learn everything that math has to offer in high school. You just learn a small pool.
Yeah. Okay, I think what we'll do is we'll take a break now. And more importantly, your brain. Maybe we'll take a little break, then we'll come back. Time is 1:40. Let's keep going at 1:50.
I was gonna say, I never heard your phone go off.
I didn't?
I never heard it.
Oh, no, it did. Yeah, this is 1:40. Yeah, because we're leaving in an hour. Yeah, okay. I might have stopped it real fast. So who do we need? We need Gabe. It's not here.
Omar.
Omar. It's not here.
You still got any of this today? They're on. I know. I mean, that is the only system you guys work.
No, it was a work. I had problems.
Well, what area was it?
We'll be done with this semester.
Are you going to see it? What about you? Sounds good. Do you guys, should I put like a little final thing for you guys to like work on as well?
Oh my God, yes.
Which is, see me? 'Cause I've done it before, that's no one's going to see me. I think came out to see me once for like, what, 10 minutes? 20 minutes? I know, it was a short period of time, but yeah.
And then you had to leave.
Oh.
Well, I had to leave at 12. My time ends at 12.
Wait.
Whatever time you guys, whatever time you guys make the decision, you guys make the final decision, you guys let me know. If it works with my time, we'll do it. If it does not, we'll find another time that will work, and so we have fun. So
Yeah, that's for the final, right?
it's for the beginning.
Oh.
You're all frustrated, like,
All right.
oh my God.
All right, buddy.
Yeah.
You ready for this?
No.
What part of London is in Brazil?
Can I see a map?
There's no part.
There's no part. A part or a part?
What part of London is in Brazil? What part of London is in Brazil? Yeah.
London
So
is
what
not-
part of London is in Brazil?
None of it.
He says none. Over you go. Yeah.
Wow. You got it.
That's true.
Geography, that sucks.
Okay, that does not make you. I know. How many months? What?
How many?
How many months?
You said it does not make you feel stupid. It's what you said. Did you hear my question earlier?
There's
But
no
they-
real
I
true
know,
measure
right?
of intelligence.
I was like, February, duh. Like that too.
He's like, every 2
Every, and I was like, every 4 years has pretty much. And he's like, every month.
He got you again.
You guys like my jokes?
It's online, it's in the announcements, Zama has extra copies. Here's the money. Oh, you put them Oh, the last one, doesn't
Just think so long.
No, sorry, me regreses a estudiar. Te lo voy a dar a tu casa. Se le recibe.
Hey, this looks really good.
Aquí está. You know, like, this isn't his fault. It's his fault.
Our finals tomorrow, right? I mean, not tomorrow, next week. Monday. Our finals?
Your test. You just have a test on it.
Okay. That's-
Desde hace 2 años.
¿Cómo puedo?
So, for our physics final, our truck is up in the-
It's not getting practice test? I never got any practice tests in my math class.
We have to go over all of our, all of our scientific.
Not as ideal as a practice test, I'll give you that. But it is to be expected. To be honest, when I get practice tests, I'm being nice. Going easy. In the classmate right now, she didn't even give us a study guide. Nothing, just that test. So all you can do is just go over all the homework you've already done, reread the textbook a couple of times, I mean a couple of times. You know how many times I read the textbook? Okay, no, not. I read the textbook at least 3 times. And that's, I read the textbook 3 times. You know how many times the average student reads the textbook? No. Yeah, so, I mean, again, I know that it comes down to time, right? Who has the time? The things you make for it, you know, anything in your life, you want time for, you make time. You know, everybody has different goals, you know? Some students want to have a goal of getting an A. That requires a certain amount of time. You have a goal of making a B. It requires less time. Have a goal of C. It requires even less time. There's an open extent of
Te estoy diciendo.
What? Where'd you get that?
Oh, you
You went all the way to the end?
my wife.
You didn't say your mom.
No, I'll never use it.
Really awesome.
But,
Wait, what do you got against Obama?
not even, don't even be talking about politics in here.
Okay.
Pero no.
Other than that,
Pero no.
that was a good.
But I asked them what part of London is in Brazil.
Brazil's in South America. London's in Europe.
You like that one though?
I'm actually, I'm pretty angry. I don't know why, but I am. Oh, man.
Actually, I went to my wife last night, and she hit me for it.
All right, folks, here we go.
I have a question.
No, she hit me because I told her like she didn't like it.
Okay. How did you go from 3 halves to 6 halves?
Because I used the definition of factorial, which I just erased. 3 factorial is 3 times 2 times 1, which is 6. And 2 factorial is 2 times 1, which is 2. So, using the definitions that I had on the board, I simply substituted the numbers. And so that was 2 over 1, and that was 6 over 2, and that was 24 over 6, and I was literally just taking the numbers right off of what I had.
Oh, I get it.
All right,
Okay,
good.
Thank you.
Good, Olivia, great.
Thank you.
Okay, so we're going to continue working on restructuring our answers. And, you know, one very interesting philosophical perspective you could take on this is that in mathematics, we never solve anything. We just keep rewriting and rewriting and rewriting things until it's in a way that we like. So like take a look at number 8 plus 11 plus 14 plus 7 plus 20. So we've got this sequence, 8 plus 11 plus 14 plus 17 plus 20. And I want to rewrite all those numbers using a similar structure. I want the structure to be the same. So how do we do that? Keep in mind that I want somehow to input the number 1, because that's the first term, second term, third term, fourth term, fifth term. So what we're looking for is a formula or a structure that if I plug 1 into it, it equals 8. And if I plug 2 into it, it equals 11. If I plug 3 into it, it equals 14. And if I plug 4 into it, it equals 17. So the first thing we do is just figure out, is this arithmetic or geometric? So are we adding over and over or subtracting over and over? What do we add? What are we adding to go from one number to the next? Sí, tres. We're adding 3. Right? Does everyone agree? You agree? Really, really, really? Okay, so we're adding 3, so that means our common difference is 3. We also know what our first term is. Our first term is 8. And what we'd like to do is come up with a formula. Well, the amazing thing is here that if we're saying it's an arithmetic sequence, and we know the first term and d, we have a formula, the explicit formula for an arithmetic sequence. It is a sub n equals a sub 1 plus d times n minus 1. And so the nth term, which is the structure we're looking for, the nth term is the structure of the nth term, that's the structure, is 8 plus 3 times n minus 1. And so from there, we just do a little simplification. That's 8 plus 3n minus 3. And we get a sub n is equal to 3n plus 5. That's the structure. 3 something plus 5.
Have you ever ran into the opposite? So like where the term you want to give us on the first term was the 10th or
Sure.
5th term.
Yeah, then you'd have to, like if that's what you knew, then you'd have to plug it in that particular value for n maybe. Yeah, perhaps. Okay, so what does that mean then? This is our structure. And now let's just test the hypothesis. Do we actually get these numbers? If I use the structure 3 something plus 5, 3 something plus 5, 3 something plus 5, 5. Does it give the numbers that we expect? So for instance, here I would plug in a 1 because it's the first term, 2 because it's the second term, 3 because it's the third term, 4 because it's the fourth term, 5. We're really just testing our hypothesis right now. I mean, we should feel good that this is correct. Yeah, it works. That's 8, that's 11, that's 14, that's 17, and that's 20. So yeah, it works. That's our structure. So since that is our structure, they're asking us to put it in summation notation. We would just say, we're doing the summation from n equals 1 through 1, 2, 3, 4, 5 of the structure 3n plus 5. And that's it. So we were given some numbers. We wanted to be able to rewrite them in the same structured form. We noticed it was an arithmetic sequence. So we were able to find the common difference and then put it into our explicit formula. That gave us the structure we wanted. And that's literally what goes into the sigma notation.
And you did that just to double check.
I did that just to double check. Yep, that's right. Solamente porque quiero ser correcto. Is that right?
Yeah.
Is it right? Okay. Okay, so how about the next one? This next one's a little more tricky, folks. I'm just going to tell you right up front. There's no reason why you should be able to exactly know this one, because I'm going to teach you a trick. Because what's different about this sequence? Yeah, you go add plus minus, plus minus, plus minus. So we need to learn a gimmick. And the gimmick is, how do you create a structure that alternates signs from plus minus, plus minus? Because it's not enough to just say it verbally. Change the sign. You have to have a structure that does that. So let's look at our numbers. This is 1, and then minus 2, and plus 3, minus 4, and plus 5, and minus 6, and plus 7, and minus 8. First of all, this is not arithmetic. Because first we subtract 3, then we add 5, then we subtract 7, then we add 9. So no, it's not arithmetic. We can't use the formula we had earlier. But we can still say, I want this to be my first term. This is my second term. This is my third term. And this is my fourth term, and this is my fifth term, and this is my sixth term, and my seventh term, and my eighth term. So we should be able to say pretty clearly the nth term will have what number in it? What number will be in the nth term? N. Right? If the eighth term is 8, then the nth term will be n. So that's the structure is n. And then what we notice is which numbers are negative.
All of the even ones.
So the even numbers are negative, but the odd numbers are positive. So here's the trick. The gimmick is that we want our number, our formula, to be n. But we want the sign to alternate. And the way you do that is by multiplying by -1 to the power of n. So this is the gimmick, is that if you want the signs of your sequence to alternate plus minus, you multiply your structure times -1 to the power of a variable. So let's see how that works out. Let's let n equal 1. If n equals 1, we would have 1 times -1 to the 1. What's that? That's -1. Is that what we wanted? The first and plus 1. Let's try that again. Write down our formula, our structure now is n, because we want the term in the sequence to be the term number. And then we're going to multiply times -1 to n plus 1. Let's try it. We'll let n equal 1, that'd be 1 times -1 to 1 plus 1 is 2. And what's -1 squared? Negative times negative is positive. So that worked out. We got 1. So let's try letting n equal 2. In that case, we have 2 times -1 to the 2 plus 1 is 3. What's -1 times itself? 3 times. A negative times a negative is positive, times a negative is negative again. And that's -2. Is that what we wanted? Yeah. Okay, and so on and so forth. We now plug in n equals 3. That's going to be 3 times -1 to the 3 plus 1, which is 4. And what's -1 to any even power? Positive. Because if you multiply -1 times itself an even number of times, each negative times negative becomes positive, and so that's positive. What happens if you take -1 to an odd power? It's going to be negative. Okay, so we have our formula. So we would just say sigma notation from n equals 1 to 8. Now again, nothing about that was intuitive or obvious. It's just a gimmick that you learn at some point, that if you want the sign of a sequence to alternate plus minus, you do -1 to the power of n or n plus 1, depending on if you want the even terms negative or the odd terms negative. And Emily, this was just me checking.
Okay, I want to ask my mom.
Or this is just me checking to fiddle with the formula, make sure I got it right.
How do you get it?
Well,
Just like,
I know that the formula is just n because the number itself is the term number. So if I want the 8th term, the number will be 8. So the formula is just n. Not a very interesting formula. It's almost so counterintuitive. Like, what? But yeah, the term number is just n. And then otherwise, we just needed to alternate the signs plus minus. And multiplying times -1 to the power is the gimmick for that. That's how you make that happen.
and then n is 1.
And then this is your counting number. You're saying let n equal 1, then 2, 3, 4, 5, 6, 7, 8.
If you were to start like from 5, then n is 5.
Yeah. Yeah, depending on where you start. Okay, let's go straight to the next one that's alternating signs. Let's look at the pattern on number 7. In number 7, it goes +1 minus a 4th plus a 9th minus a 16th plus a 25th minus a 36th. Now, I'm going to use the should word on you. I'm going to should on you. You should all recognize the numbers 4, 9, 16, 25, 36. Because we've already used them a couple times this hour. What are the numbers 4, 9, 16, 25, 36?
Square root by n.
Well, squares. Yeah, they're the square numbers. Okay, so first of all the numbers are fractions, right? Except for
1.
So let's make that a fraction. Because we want the numbers to be as visually similar as possible. We don't want to mess around and leave things to like almost.
Why did we skip 6?
I wanted to go to another one that alternates signs. So I said, let's go straight to 7 because it alternates signs. Or what? No, we're not crossing it off. We're just doing this one first so you can get more practice with the negative. Okay. Now, just like we were doing before, we want to rewrite all these numbers in a structure so that the structure looks the same. So we rewrite these now as positive 1 over 1 squared minus 1 over 2 squared plus 1 over 3 squared minus 1 over 4 squared plus 1 over 5 squared minus 1 over 6 squared. Notice what we're doing right now is we're just rewriting. We're rewriting to make the pattern more painfully obvious. Now again, in terms of linking the structure to the term number, we're saying this is the first term, and it's 1 over 1 squared. The second term is 1 over 2 squared. The third term is 1 over 3 squared. The fourth term is 1 over 4 squared. The fifth term is 1 over 5 squared. The sixth term is 1 over 6 squared. So what's the nth term? 1 over n squared. Does everyone agree?
Yes.
Okay, so far that's our structure. We have the structure 1 over n squared so far. That would give us the pattern, but not the alternating signs. So how do we give it alternating signs? We multiply times negative 1 to the power of n, or n plus 1. We have to figure out at negative 1 to the power of n, or to the power of n plus 1. You have to figure out which one to use. So it's either going to be n or n plus 1. So we just try one to see if it works. If we let n equal 1, we want the first term to be positive. So if I let n equal 1, so let n equal 1, that's going to be 1 over 1 squared times negative 1 to the 1. That would be 1 times negative 1, which is negative 1. Do we want the first term to be negative 1? No, we want it to be positive. So it has to be n plus 1. It's either n or n plus 1. So now let's try n plus 1. Then if we let n equal 1, that's going to be 1 over 1 squared times negative 1 to the 1 plus 1 is 2. And therefore, I have squared the negative 1. That makes it positive, and my first term is 1, and that's what we wanted. So that's our structure. So we say sigma notation from n equals 1 to 6. And that's our sigma notation for that one. All right, so that's how you make a sequence alternate plus minus. Try one more here, and then we'll move on to a different skill, which is finding the sum of a sequence. So in number 6, so everyone, we're going back to number 6. We did cross it out. We have 2 plus 3 halves plus 4 thirds plus 5 fourths plus 6 fifths. Now right off the bat, you all know what to do that number 2, right? Make it a fraction.
What is a nice sequence?
It is a nice sequence, Emily. What makes you say that? Yeah, I mean, they're counting out, right? So the key thing we need to do here is label these with the term numbers. We're saying this is the first term, second term, third term, fourth term, fifth term, and therefore we want to predict the nth term. So we need to come up with a formula for the numerator and the denominator. And I think the denominator is the obvious one, because the first term is 1, the second term is 2, the third term is 3, the fourth term is 4, the fifth term is 5, so the nth term is 10. So the denominator is just 10.
That is n over n plus 1.
The other way. So now look at the numerator. How do we get a 2 from a 1? How do you get a 3 from a 2? How do you get a 4 from a 3? How do you get a 5 from a 4? How do you get a 6 from a 5? Add 1 to it. So you're always, remember, we're trying to write a formula in terms of the term number that you're on. So if you're on the first term, it'd be 1 is the denominator, 1 plus 1 is the numerator. If you're on the second term, 2 is the denominator, but 2 plus 1 is the numerator. So our term is n plus 1 over that. And they want us to rewrite it using summation notation, so it's going to be sigma of n plus 1 over n. And the first term was n equals 1. And the last one is 5, because we have 5 terms. we go. We've talked a lot today about rewriting something in a different form. This is our last section. And it's about adding things up.
Basically our last class.
It is. This is our last class in the material. Yeah, we have a good amount of time. Folks, I want to introduce you to a phrase called cognitive complexity. Cognitive complexity. And cognitive complexity is the ability to attribute more than one explanation to something. So, nice little example that's often used in communication classes is you see someone just cut you off in traffic. So you're driving, someone cuts you off. What's your first thought? That person's a jerk. That person's a bad driver, you know? Okay, now that's one interpretation, right? And maybe you want to stick with that. But what else could it be? It could be that he was swerving to avoid hitting a dog. You know, and that's unfortunate. Maybe he would have hit you, but he was trying to avoid the dog. Worse, maybe she was swerving to avoid hitting a child. Right? Now, is this person still a jerk? Was he cutting you off? Is he a bad driver? No, he was actively trying to avoid hitting someone. The thing is, you don't know because you didn't see it. They could be rushing to the hospital. They could have somebody bleeding out next to them, and they're just trying to get there as quickly as possible, right? There's a lot of reasons why someone could cut you off in traffic. So are you 100% certain that you know for sure that the reason they cut you off is just because they're a jerk and they're a bad driver? You really don't, okay? Cognitive complexity actually blows open this huge admission that we have no idea what's going on. Right? We think we know what's going on, but we're quick to judge, but the fact is we don't know. Are they feeling angry?
Yeah.
Maybe. What's another reason they could have that look on their face? That's their face. Good one. Why else? Yeah, they could be thinking about something painful. They might not be angry at all. They could be thinking really hard. They could have indigestion. They could be having some stomach problems, and they could be really in pain right now. Are they angry? No. So again, cognitive complexity means we have no idea what's going on. And again, it's the ability to attribute more than one explanation. And so if I were to just look at the number, for instance, 64, I invite you to practice cognitive complexity. What is that number? What is it? What?
8 times 8.
It could be 8 times 8. What else is it?
It's any number that makes a number you have make it equal.
Right. Let's generate a couple. What's 64?
8 times
Very good, which is the definition of 8 times 8. What else is it?
8 times 2.
It's 32 times 2. What else is it? We could go with, obvious things like 70 minus 6.
How about this one?
Or 60 plus 4.
How about the squared, no, and that's squared root 4,096.
4,096?
Yeah.
Okay. Yeah, it could be that. Going back to some simpler ones, 64 happens to be 4 cubed. What else is it? It also happens to be 2 to the 6th. I suppose it could be other things as well.
Yeah, there's a lot of ways to do it.
Right, yeah, there are lots and lots of other ways that this could be something. In fact, it could also be, here's a weird one, 100 minus 36, which means it could be 10 squared minus 6 squared, which means 8 squared is 10 squared minus 6 squared. That's random. Okay, so do you see how what I'm doing here is I'm trying to suggest that this is an example of cognitive complexity turned to mathematics. Not just how you interpret people and behavior, but how you look at something. And the more you practice cognitive complexity, the more math problems become a little easier. Because you're not just thinking of it in one way, but you're allowing yourself to be like, okay, how else can I think about this? How else can I think about this? How else can I think? Okay, so if you're ever feeling at a dead end with something, you need to think about it differently. Right? Does that make sense? And normally the word we use for that is brainstorming. What is brainstorming? What is warming? If we understood those words, maybe we'd understood brainstorming. Okay, so you don't kidding, right? Brainstorm. Say brainstorm. Yeah. Okay, so this is a lot of what we're talking about in here is how do you look at something, but then allow yourself to look at it differently. Because the more different ways you look at something, the better off you are. Okay, so let's start. We're going to find the sum now. They give us two different formulas for sums. There's the sum of an arithmetic sequence and the sum of a geometric sequence. So we'll go ahead and practice both of them. The first two, are these arithmetic sequences?
Yes.
How do you know? mx plus b. They're linear equations. This is mx plus b, mx plus b. These are definitely arithmetic, so we're allowed to use the first formula. Now before we do, let's just take what we're given and write out the first couple terms. So we want the sum from n equals 1 to 10 of 5n plus 3. And I won't make you write out all the terms, but we'll do the first, the second, and the last. So even though we're technically plugging in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, let's just look at the first two terms and then the last term. So the structure within is 5 something plus 3, 5 something plus 3, 5 something plus 3.
Is that order you had before, 8, 13?
Could be, yeah. And now we're going to plug in the numbers 1, 2, 3, 4, 5, but I'm just going to plug in 1, 2, and then the last number is 10. Because I'm just interested in the beginning of the sequence and the end. So now that's going to be 8, and 13, and all the way up to 53. I didn't bother writing out all the terms because we don't want to have to sit there and add them all together. We'd like a shortcut, and that's what these formulas are. These formulas are a shortcut so that you can get to the sum without having to painfully go through, find each term and add them all together. So let's take a look at that sum of the arithmetic sequence. The sum formula, sum of arithmetic, so everyone should write this down in the space we have, is S sub n equals n over 2 times a sub 1 plus a sub n. Now what is this formula? N is the number of terms you have. We all know how many terms we have. How many terms we have? 10. So what we're doing is finding the sum of 10 terms. Notice the subscript now is 10. That means I'm finding the sum of 10 terms. And I'm going to let n equal 10. So now over here, I'm going to put a 10 where the n was. And inside of here, that means we have a sub 1 and a sub 10. Well, that just means literally the first term and the last term. So now what we have is 10 over 2 times the first term, which is 8, and the last term, which is 53. And the sum of our sequence is that. We didn't even need the second term, but I just put it there so that we could see the common difference in case we wanted to know it. The common difference is b equals 5. We're adding 5 over and over again. Name one other way we knew the common difference was 5. Anybody know the common difference is going to be 5? Because that's the number on the variable. That's the slope. The slope is the common difference. Okay, so add it all together, folks. We got 5 times 61, which is 305. So the sum of all of those terms, even though we didn't find them or add them up, is 305. And we got that from our formula. Now notice, to do that sum, we did need to know how many terms there were. In fact, what do we need to know? We need to know n, the number of terms, and we need to know the first term and the last term. That's all you need to know in order to find the sum of an arithmetic sequence.
This is something like you told us last class that you take the first 10 to last.
Yes, yes, exactly right. Yeah, that's how Gauss added up those numbers 1 through 100. Yep, that's exactly right. Okay, so that was number 1. Everybody do number 2. You're going to do the sum from n equals 1 to 20, 2n minus 1. Again, you can just write out the first term I'm the last term. And then turn around and do your formula. S of n equals n over 2. And I'm going to label these. Maybe you'll label it too. N is the number of terms. A sub 1 is the first term. A sub n is the last term. I just submitted my last homework assignment in my math class.
Yeah.
Actually feeling a little depressed.
Oh, why that's always
You know, you just work, and then all of a sudden it's done.
done.
You feel a little empty inside. What am I gonna do later today?
Fair enough, right?
What am I gonna do? Spend time with my family? That was a total joke.
Oh my god.
We're going to the zoo right after class.
I was like, wow, is it really that bad?
Yeah, that's just a joke.
How old are you? How old are you?
2.5.
Okay, she was still holding that, but without them.
Yeah. One of my favorite jokes to tell my wife when I hear a song on the radio that I like, I'm like, oh, I love this song. This song reminds me of a time when I was happy. It's just a joke. It's totally just a joke. It's one of our little fun inside jokes.
How does she do? Oh,
She
how does she-
Besides, that has nothing to do with marriage.
Wait.
Right? I'm just saying.
Now
it's
we
just
can
life.
feel the same way.
Yeah.
Oh yeah, my wife knows already.
Yeah. And besides, I'm far happier now than I ever was. That was just a joke. Okay, so what did you all get? The first term was 2 something minus 1, 2 something minus 1, and you plugged in 1 and 20. And so the first term was 1, and the last term was 39. And so how many terms did we have? So we have 20 over 2 times 1 plus 39, which is 10 times 40, which is 400.
So far.
Is that right? Is that what everybody has? In a minute, you will. Okay, well, that's it. I mean, the arithmetic sum formula is pretty straightforward. What makes it challenging is if they don't give it to you in sigma notation, which is what we're about to practice. The hardest thing to find, I think, is the number of terms. How many terms are there? So let's, if you don't mind, let's skip and take a look at 5 and 6. Those are arithmetic sequences, but they don't tell us how many terms there are. So this is a bit of a puzzle. Everybody, we're going to skip to number 5. Let's say that you're given a sequence 1 plus 4 plus 7 plus 9 plus 295. How many terms are in that sequence? You are very good, Melania. Thank you. I'm adding 3. So,
We also added 3 digits, something to.
right, and you can keep adding 3. I mean, how long do you gotta wait for it to go 7 plus 3 plus 3 plus 3 plus 3? It's gonna be a while, right? Okay, we don't want to actually list it out and then count. That'd be painful. So instead, what we want is a way to solve for the number of terms. Unfortunately, we have that. We have our explicit formula. And what term is in that explicit formula? N. N is the number of terms that we're looking for. So all we do is plug in what we know. And what we know is that the last term, okay, so A sub n is referring to the last term. That's, in this case, the last term. We're using it to refer to the last term because we have the last term. So now we're saying the last term is 295. The first term is 1. The common difference, Valeria told us, is 3. And now look what we have. We have a formula that we can solve for. Solve for what? N, which is got a number of terms. So we took our explicit sequence formula for arithmetic sequences, and we're just going to go ahead and solve for n. So I subtract 1, 294 plus 3, 1. That's 98. equals n minus 1, so add 1, and n is 99. So the number of terms is 99. Notice that was the only thing we needed to find. Because now, if we just go back and look at our sum formula, s span equals n over 2 times the first term plus the last term, we already had the first term and the last term, right? That was given to us. They gave us the first and the last term. What we didn't know was just n, but now we know n is 99. So the sum of 99 terms is 99 over 2 times 1 plus 295. Does that make sense? So you type all that into your calculator. I got 14,652. That's a surprisingly large number, 14,000, considering that the numbers we're adding up are just up to 295. But just imagine you're adding up a lot. So now you can all try number 6, because it's the same thing.
So what is the 14,000?
That's the sum. That's what it actually adds up to. That's what we're trying to find, is the sum. Yeah, that's the summation formula. So I might be able to try number 6 using the same approach. Then we're looking at it, we're like, okay, if I wanted to find the sum, I would need to know the number of terms and the first term plus the last term. Again, see, I want to kind of role model how you think this through. You'd say, okay, I want to find the sum. So, by the way, is it arithmetic? What are we adding every time? Yeah, -2. I'm always adding -2. So it is arithmetic. So we can write down the arithmetic formula. And we don't know what n is, so I can't plug in the n, but I know the first term is 4, and I know the last term is -146. So you can see we're really close. What's the only thing we need to find? Yeah, the n value. And so where are we going to go to find the n value? The explicit formula for arithmetic sequences. Because now again we can plug in the last term and the first term and the common difference. And that gives us a formula we can solve for n.
So for this type of problems, you have to use both of them.
Yep.
Are you gonna use it?
I wasn't planning on it, maybe.
Are
But
you sure it's a lot?
Because I was trying to stay away from it.
Yeah, it's a
Well,
lot.
I didn't tell the other class that they would get a formula sheet. So I think it's reasonable to ask you to memorize them, but I'll think about it. Your request has been duly noted, maybe.
36.5. Hey, Mr. G, does that sound right? This one is 36.5 when you divide the 146 and 4.
But n has to be a whole number.
I got to be 4.
N has to be a whole number.
What?
Because n is the number of
Just say
terms.
40, 37.
Yeah, that works right, Bobby. Although, isn't that a negative 146? And isn't that a -2?
Can you subtract?
Oh, no, you can't do that. No,
No?
because
Okay.
this 2 is being multiplied by n minus 1. You have to think n minus 1 is being multiplied by -2 and adding by 4. So you first have to subtract 4.
Okay.
But that's a negative 146.
Okay.
So folks, looking at your algebra, we want to solve for n. So you tell the story of n. You say n is being subtracted by 1, multiplied by -2, and adding by 4. What would you do first? Subtract the 4. Oh. It's imperative that when you're doing algebra, you look at the algebra, or you look at the variable and tell the story of the variable. That's not an optional step. You have to stare at the algebra and say, what's happening to it? It's being subtracted by 1, multiplied by -2, and adding by 4. That's not an optional step. That's the definition of algebra. Now you're adding by 4, so you subtract by 4. That gives you -150 equals -2 times n minus 1. And you'll notice now you just do the same thing all over again. You look at the variable n and you say, what's happening to n? N is being subtracted by 1 and multiplied by -2. So divide by -2. So now you have 75 equals n minus 1. And you proceed again to say what's happening to n. N is being subtracted by 1. You add that. What's that mean? So look at your algebra very carefully. Make sure you copy down those steps so that you can study those steps. Good.
I have a question. Is the inside part which is n minus 1, is that always going to stay the same?
Yes, because that's the formula for the explicit. That's the explicit sequence formula. All right, so now we know that n is 76. So we can come on back over and say we want the sum of 76 terms and then plug in the 76. Yes, Emily, thanks for the question. You would need to use both formulas because you have two unknowns. Your first unknown is how many terms are there? Your second unknown is what's the sum? The number of questions you're answering tells you the number of equations you'll need to use.
Number 7 is tricky. Because you're not even dealing with full numbers in the first place.
That's true. And plus number 7 is geometric, actually. So we'll need to switch over now and think about what is the sum of a geometric sequence. And this is our last skill, people. We have 20 minutes. This is our last skill. Skill. I understand. I'll have tissues available after class if you want to have a good cry. No, Mr. G.
What does all the Rubik's before the test starts?
Yeah, there you go. All right, so we want to find the sum. Okay, so everyone, we look at number 3 and number 4. We'll start by looking at number 3. The number 3, let's just understand the question first before we start thinking about this new formula we have. In number 3, we're looking at sigma from n equals 1 to 10. So there are 10 terms, and each term is 1/2 to the power of n. So what are we looking at? That's 10 terms, and the terms are all simply 1/2 to a power. So that's going to be 1/2 to the power of 1, plus 1/2 to the power of 2, plus 1/2 to the power of 3, plus 1/2 to the power of 4, plus 1/2 to the 5th, plus 1/2 to the 6th, plus 1/2 to the 7th, plus 1/2 to the 8th, plus 1/2 to the 9th, plus 1/2 to the 10th. Right, so does everyone agree that's what we're looking at?
Yeah.
Okay. Now, if we just rewrite these real quick, that's 1/2 plus a 4th, plus an 8th, plus a 16th, plus a 32nd. And now, do you all recognize this formula for the first day? Not including you, Nadine, because you weren't here. But you are included, Nadine. You just wouldn't have recognized it.
Magically remember.
Okay, so there we go. You remember the sequence? I said, what if we added these up forever? Infinitely many terms. What if we added a half, plus a fourth, plus an eighth, plus a 16th, all the way to infinity? What would it add up to? 1, right? So if you have any finite sequence, it doesn't add up all the way to 1, which is really 0.9999999 forever. So what is this thing going to approximately add up to? Quite a few nines, you know, and then maybe, you know, something, right? So reasonably, we already know what the answer is. Like if somebody came up to you and they're like, hey, what's this add up to? You could just kind of like, all casually be like, 0.999, right? Because you already kind of know roughly. It's going to add up to almost 1, right? But that's not enough to just jot down a bunch of nines. We need to know exactly how many. So there's a formula they give us, and the formula states that if it's a geometric sequence, well, first of all, is this a geometric sequence? What do you multiply by every time to go from one term to the next? Well, multiplying by 1/2, because to go from here to here, this is 1/2, that's 1/2 squared, you multiply by another 1/2. To go from 1/2 squared to 1/2 cubed, you multiply